So in this section, we're going to consider the electrostatics of PN junction. And what I mean by this is just the quantities like the depletion width, the built-in voltage, and where the charge densities are. So the PN junction is formed by taking a piece of N-type doped silicon and bringing it into contact with a piece of P-type doped silicon. So here's our N side, here's our P side. On the P side, the Fermi level is here, somewhere below the middle of the band gap. On the N side, it's here. And I'm going to denote the Fermi level on the P-type side with another subscript P and a Fn for the Fermi level on this side. So in this case, we're not talking about excess carriers. We're talking about equilibrium carrier densities, but I just have to denote which side we're talking about. So essentially what's going to happen is some electrons are going to transfer across from this side into here, and some holes are going to transfer across from this side into here. And we have our donors on this, the N-type side. So we're going to end up taking those electrons away from those donors and putting them into this P-type side, leaving behind charged donors or ionized donors. Similarly, on this side, we're going to end up with some ionized acceptors which carry a negative charge. So as you look at this diagram, the only way I can get the EFN and EFP to be equal is to take the bands and sort of shift them like this. And indeed, that's what happens. The end result is that the band diagram introduces some bending into the energy levels. So here's our EC, and our EV as a function of distance x. And now we can enforce this constant Fermi level across both sides. Now, we can calculate the amount of band bending, meaning the magnitude of this built-in voltage, using a few different energies as reference. So in a lot of cases, it'll be convenient to use this energy difference. So here it's the phi sub n, which is the difference between EI and EF on the N-type side, and phi sub p similarly on the P-type side. So here I've drawn EI. And you'll notice that because EI has a constant position within the band gap, because it's defined for the intrinsic semiconductor irrespective of doping, we can use it as an energy reference, and the shape will be exactly the same as that of the conduction band or valence band. So we can write the built-in voltage here as phi p plus phi n. Now, we're somewhat more used to expressions for carrier densities which use this difference here, this EF minus E sub V, or similarly on this side, I could calculate my N from EC minus EF here. So you can choose to calculate the energy differences a few different ways. If you choose to use the E sub I as a reference, it's a little simpler because the built-in voltage is a simple expression like this, whereas the built-in voltage, if you write it out in terms of the band edges, also has to include E gap. So the expression gets a little more cumbersome because you have to write E gap over Q minus this energy difference here. So the expression's a little more cumbersome. You can do it this way, though. Okay, now we're going to want to come up with expressions for the difference between the Fermi level and the intrinsic Fermi level on both sides of this p-n junction. So first, we'll insert our intrinsic Fermi level on both sides. And on this side, we'll say that our n naught is given by our donor concentration. And on this side, we'll say that our p naught is given by our acceptor concentration. So we're assuming full ionization here. So the quantity we're looking for is here and here. So first, let's express the carrier concentrations. N naught is Nd, and this is going to have to be Ni exponential to the EF minus E sub I over kBt, and P naught is Na, we're assuming, and this is a similar expression. Except on this side, the Fermi level on the p-type side is below EI, and on this side, the Fermi level on the n-type side is above E sub I. So the next step is to solve for these energy differences, which we do by inverting these equations. And so we have Na over Ni, take the logarithm, multiply it by negative kBt, and this gives us our EI minus EFP, and similarly minus kBt logarithm of Nd over Ni gives us EF on the n side minus EI. And these are our quantities that we're looking for. So now we can go ahead and calculate the built-in voltage. Now we've made another assumption here, which is that these expressions here are valid, which means that we've assumed non-degenerate doping. So sometimes we'll have so-called one-sided diodes, which we'd represent as P plus N or N plus P. And in these cases, this means that the P doping is much, much heavier, let's say a factor of 100 or more, greater than the N-type doping on the other side, and vice versa. Something like 100 times bigger than the N-type doping than the P-type doping for this. And as we go through and look at the depletion widths, we'll see that the majority of the depletion width, in fact, given by the ratio of the dopings, will be absorbed in the N-type side in this case, and in the P-type side in this case. So the depletion width will always be primarily in the side which has the lower doping. Now, if this is true, if we actually have P+, what does this mean? So P+ would be a situation where we could assume that the doping is degenerate on the P-type side. So for a P+ piece of material, we would say that EFP is equal to the valence band edge, and similarly, EFN would be equal to the conduction band edge in the case of N+ doping. So if this is true, how much voltage, built-in voltage, comes from this side? So we only have to look at this diagram and we can pick it right out. If we assume that the Fermi energy is right at the band edge, well then the amount of built-in voltage that you can get from that side is equal to EI minus EV, or simply EI if we set this equal to 0. So when we go to express the built-in voltage, I want to introduce the idea that what we're doing is adding the built-in voltages from the two sides. And we use these expressions here if the doping is non-degenerate. However, if we have P plus doping or N plus doping, we'll just assume that the band edge, that the Fermi level on that side is exactly at the band edge, and we'll set this equal to the band edge minus the position of the intrinsic Fermi level. So if we make the assumption that it's non-degenerate, on the N-type side, and I'll do a mixed case here. On the P plus side, we would have an expression like so. We would have negative kBt logarithm of nd over ni coming from the N-type side, and then we would add simply E sub I divided by Q, because remember that energies are voltages times the charge. So this would be the case for this mixed case of a P plus N junction. And then you could figure out what would happen for a junction that's degenerately doped on both sides. Well, the built-in voltage would be this plus this, or exactly the band gap, if we had P plus N plus, the built-in equals E gap. And if we just have a simple Pn, then V built-in equals negative kBt logarithm of nd na over ni squared. Okay, so those are our main cases for the built-in voltage of PN junction, including one-sided diodes. So now let's look at the consequences in terms of actual charge buildup and electric fields. So now we're going to lay out the equations we're going to use, and then the quantities we need to define to solve the electrostatics of the PN junction. So our band diagram will look like this. And what we're going to do is define a region over which we're saying we have no free carriers. So this is the metallurgical junction. Where the N-type side and the P-type sides come in contact. We have our Fermi level, which is constant across the entire junction. And we said that we're going to have ionized donors on this side and ionized acceptors on this side, making a actual charge density that's positive on this side and negative on this side. And then finally, we're going to have to invoke some formulas from electrostatics. So the first equation we're going to use is a version of Kirchhoff's circuit law. So we've already sort of calculated the built-in voltage from simple arguments looking at the change in the Fermi level. I'm going to introduce a procedure now which will allow us to analyze more complicated junctions as we go forward in the class, especially heterojunctions later. So the idea is you pick a point, an energy, and start there, and then go around a closed loop, coming back to the original point. So we have to add now our intrinsic Fermi level, which we'll use as our energy reference. And let's start on the Fermi level. So the first thing we can do is start on E sub I here, go down to the actual Fermi level. So this gives us our phi sub p on this side. So we have minus phi p. Then we subtract off another part, which is going to be given by EF minus EV then if we go all the way down here, we get the built-in voltage, which is the thing we're going to look for, minus V built-in. Now we're on a constant line where we can come over all the way to far through the junction to the other side, far away from the junction on the N-type side, where we add, so now we add, plus EI, then we add our phi p, I said it. So I meant phi sub n, Then we can come back over on this Fermi level line and end up back here where we can take off that phi sub p again, minus phi p and equals 0. Now I did a little bit of duplication here to make sure that I highlighted where phi p is and where the Fermi level is with respect to the valence band edge. So we're going to take these out there, and then we have to deal with this term, but we can rewrite this term actually as the EI being the sum of these two. And so we can rewrite this here as EI minus phi p, and then we put the whole thing in a negative there. And then let's bring this V built-in over to the other side. And then we have plus EI plus phi n. Now we can clearly cancel this and this. This becomes a plus sign, and we're left with this expression here, and I just remembered that I need to multiply my voltage here by Q because these phi's I expressed in terms of energy. Okay, so our phi's here we're going to consider as voltages as well as this voltage, so we're multiplying by the electron charge to get electron volts. Now this might look like a little bit of overcomplication. However, when you start going into heterojunctions where you might have a conduction band edge discontinuity, this procedure becomes very useful, and so I've introduced it here. So now for our second equation, what we're going to use is the idea of charge balance. That when we pull electrons from the right-hand side here, they have to be balanced by the same number of holes coming from the p-type side. So the total charge on the p-type side has got to equal the total charge on the n-type side. And this means that Q times NA times the width here on the p-type side. So the contribution to the depletion width coming from the p-type side has got to be equal to Q times ND times Wn. Similarly, we define this as W sub n. Now I've assumed here that the dopants are all completely ionized in making this equation, sorry, this expression of this equation right here. At lower temperatures, you could express these as the thermally ionized fractions of the total dopant concentrations. So what this equation means is that if the doping on the n-type side is higher, it means that its depletion width has to be smaller. And this here would represent an area on a graph of charge density Q as a function of x. So I put Wn there. Here's my ND, and let's imagine that our number of acceptors is lower. It would mean that the depletion width would have to extend further in the negative direction in order to make sure that the area of these two boxes was the same. So the charge balance equation says that these areas have to be the same. Now in the limit of, let's imagine that ND goes up very high so that it's degenerate doping, and we call it N+, then this depletion width will be very, very small. And that would mean that the depletion width would be almost entirely on the Na side. So you can express the ratio of dopants Nd over Na is going to be equal to the depletion width on that side over Wn. And then if we express the total depletion width as the sum of Wp plus Wn, we can substitute in, for example, we can substitute in for Wp in terms of Wn and then work out an expression for Wd as a function of the doping on both sides. So now we need to come up with our third and final equation that links the voltages to these charge densities that we've figured out. So here's our equation 2 in a compact form. So our equation 3, we can connect the charge density to the voltage by using Gauss's law. So we can say that the double derivative of the voltage equals the charge density Q of x over 4 pi epsilon relative epsilon naught. So that means we can start with the charge density, integrate once to get the electric field, and then integrate again to get the voltage. So we can carry out this integration over this constant charge density in a piecewise fashion. So for example, we could get the electric field as a function of x for points between negative Wp and the metallurgical junction. We'll get and I'm setting my x equals 0 here at this metallurgical junction. So we're going to be integrating over a charge density given by Na times Q dx. And then we pull out the 1 over 4 pi epsilon relative epsilon naught. Now if instead we want to go to a point that's not all the way to the metallurgical junction, we could just replace that limit there with x. So now let's assume we're going to actually cross past the metallurgical junction. I'll put the 0 back in there and write the expression for the other side. We're going to have the 1 over 4 pi epsilon relative epsilon naught times the integral from 0 to x now of q and d dx. And looking at this, I've forgotten a negative sign right there. So on this side, the charge density is negative because we have ionized acceptors, and on this side, the charge density is positive because we have ionized donors. So this would be on the n side. So we could find out that our maximum electric field magnitude, although it is negative, will occur at the point x equals 0, and it would be the value of this integral here. It would be simply equal to 1 over 4 pi epsilon naught, epsilon relative, times q and a, and it's negative. So because we've integrated a constant function as a function of x, here's our E field magnitude, and it's going to go down to a point E max here. And it starts at negative WP. And let's say it goes over to the point Wn. So doing the same integral on this side, I need to get the same answer because the E field has to be constant valued at x equals 0. It doesn't have to be continuous. In fact, it is cusp-like or discontinuous. It reaches this maximum point and then goes down linearly as you integrate through this opposite charge density. So we have some useful expressions here. And we see that the E field increases from 0 all the way to a maximum value, and then returns to 0 on the other side of the depletion width. So now finally, let's integrate this one more time so we can connect this charge density all the way up to the built-in voltage. So in order to get the built-in voltage, we should actually write down the functional forms of these two lines. So this line here is, you can write it in the form y equals mx plus b, where our b here is our negative Emax. So we have E as a function of x on the p-type side equal to the slope, which is given by just the constants here. So negative q Na over 4 pi epsilon relative epsilon naught. And then our intercept is actually negative Emax. And this is P side. And on the N side, we're going to have a similar expression, except we're going to have a positive slope. So E of x is given by positive q and d over 4 pi epsilon relative epsilon naught times x, and then again minus this Emax. And I just inserted the x that I forgot there. This has to be in the form mx plus b. Okay, so if we integrate in order to get the voltage, we're going to use the relationship voltage as negative integral of E of x dx. And what we're going to get when we integrate this side here, sorry, let me start with the p side. So we'll get, pull out the constants, negative q Na over 4 pi epsilon naught epsilon relative times x squared over 2, and then minus Emax times x. And we're going to evaluate this. We're going to now carry out our integration from the edge of the depletion width to 0, so negative WP to 0, and we're going to evaluate it similarly. So the total built-in coming from the p-type side is given here, and what we'll get is 0 minus Emax times 0, and then plus QNA over, 8 pi epsilon relative epsilon naught, and then WP squared, and then plus Emax WP. So this describes a parabola if we integrate from any point negative WP up to any point within this p-type region. So this gives us this curvature here. And then if we go all the way to 0, we get this result. And then we can start our piecewise integration on this side using this function here. So our total built-in voltage is going to be this quantity here. So Q NA over 8 pi epsilon relative epsilon naught WP squared plus Emax WP, and then we're going to add the integral from 0 to x of this function here, Q and D over 4 pi epsilon 0 epsilon relative x minus Emax. When you complete all of these integrations, the last result is that and simplifying the result, you have that the built-in voltage is given by the charge Q over 2 epsilon 0 epsilon naught times ND times Wn squared plus NA WP squared. So this is our final form of our equation that we got using Gauss's law. And now we have an expression that relates the depletion widths on the N and P sides to the built-in voltage. Our second equation, remember, was that Wn and D has got to equal WP and A. So now we know how to relate these two parts to each other. And then our final equation is V built-in has to also equal the phi n plus phi p. So now we're in a position where we can solve this system of equations for all the variables that we need. So in the next little segment, we'll look at the expressions for the depletion width and what happens to that depletion width when you start to apply some voltage.